Hello friends. So today we'll try to understand the concept of energy quality. So first of all, we'll take up the energy. So there are actually in thermodynamics, in the field of mechanics or classical mechanics, energy is divided in two categories. Energy is whatever uh, can give a motion to a system is called energy, mainly with respect to the thermodynamics and the mechanical engineering aspects. So, in that respect, energy can be categorized into parts. First of all, that is high grade energy, and the second one is low grade energy. Uh, High grade energy, we can take the examples like work. Work is a type of high grade energy, then kinetic energy, then potential energy. These are the types of high grade energy. What about low grade energy? Low grade energy is basically the heat. So how are we categorizing these energies? Actually, the thing is that uh, this categorization is based on the humans. I mean, because humans have categorized these types of energy. So these are the basis of their usefulness. I mean, whatever the energy humans can use for their purpose is called the high grade energy. And the energy, I mean, totally humans can use these types of energy for their purpose. I mean, totally for their purpose. Then that is called high grade energy. And whatever energy humans cannot use totally is called low grade energy. Or in other words, we can say that uh, so actually one more thing is that these high grade energy is also called available energy. Fine. And this low grade energy is the combination of two energies. First is available energy and second is unavailable energy. So try to understand what is available energy. If we are saying available energy, so what is that available energy? So available energy can be converted as a form of force. Whatever energy we have, if we can able to convert it in the form of force, then that is called available energy. And whatever energy which can't be converted as a form of force is called unavailable energy. So as I said that this categorization is based on the human purpose, because force basically use uh, humans. I mean, humans use this force because of their purpose. I mean, for rotation of machine and lifting something, lowering something, pushing something, stretching something. For that purpose humans use. So on the basis of these categorization are given. Fine. So in thermodynamics, we we study the first law. So first law is called the quantitative law. First law is called the quantitative law. And what is second law? Second law is called the qualitative law. So in this topic, we basically deal with the qualitative aspects of the energy. I mean, in the first law, we have calculated and we basically use the calculation of energy, that how much energy we are getting from anywhere, and how much amount it is converted to different forms of energy. It may be that heat to work or internal energy, whatever. But in second law, we basically study that whatever energy we are getting, how much it can be converted into our useful work or for our useful purpose. That's why here the in topic comes into the picture. So if I talk about the high grade energy, so for high grade energy, entropy basically remains zero, or change of entropy basically remains zero, or I should write it like not E, I should write S, because it is defined with S, so I should write it S. And for the low grade energy, entropy actually is proportional to unavailable energy. Now you will get some idea that what is the unavailable energy. Unavailable energy is the part of that energy which can't be converted into the work. That's why here the entropy comes into the picture. We'll understand it better in further slides. So first of all, I will here talk about the thermal energy reservoir. What is thermal energy reservoir? So it is called a source if it can supply energy, and it is called sink if it absorbs energy. So thermal energy reservoir means the temperature remains constant during the interaction. That whatever we have the reservoir, let it be a source. If we are getting some amount of energy, then its temperature must be constant. And if we have a sink which is getting some heat, so its temperature should be remain constant, then that is comes into the category of reservoir. Okay, now as we have started the concept of energy quality, so energy quality comes into the concept of the second law of thermodynamics. So I will discuss the second law of thermodynamics. Fine. So if I am saying that law, so what is that law? What is that law? So actually, the second law of thermodynamics basically deals with the qualitative aspects of energy, but this is not the law. So law is given by some person which have studied or researched on something. So the law basically this law is given by different persons. So first scientist which have given this law is called the Kelvin Planck. Kelvin Planck. So that law is called the Kelvin Planck statement. Fine. So this can be given as like it is impossible to develop a cyclic device which exchange energy with a single reservoir and develops net work output. Fine. So it is just saying that let's say we have a reservoir. Let it be a source. And if I'm saying that we have a reservoir and I'm getting heat from this reservoir, and I have made a cyclic device which is producing work continuously, it means that Q is converting into work. It is developing network output. So this is not possible. This is the Kelvin Planck statement of the second law. This is not possible. So the concept of such a device will have 100% thermal efficiency. How? Because if you will calculate the efficiency, let's say eta is equal to 1 minus T2 upon T1. T2 is the sink temperature, and this is the source temperature. So we don't have sink, so this temperature is 0, where T1 which is equal to 1 means 100% efficiency. So 100% efficiency is not possible for any device. So this is called, if we have made I'm talking about such type of machine, so that type of machine is called PMM2, or perpetual motion machine of second kind, which is impossible. Fine. In other words, I can define that efficiency. If I talk about efficiency, then efficiency for a heat engine is basically what the work is it is producing and what the heat it is taking. So if I talk about this type of perpetual motion machine, then all the heat it is converted into the work. So it means that Q upon Q, which is equal to 1, means 100% efficiency, which is not possible. So what is possible? uh, the possible thing is this: if we have a high temperature reservoir and also we have a low temperature reservoir, and if we are taking some heat from the high temperature reservoir and giving some amount of heat to the low temperature reservoir, then the difference of these heat can be converted into the work. This cycle can be possible. So here efficiency will be desired effect upon whatever energy we are giving, that is heat input, which is W upon QH, or we can say QH minus QL, that is W upon QH, or we can say efficiency is equal to 1 minus QL upon QH. This is possible. Fine. Now the second statement, because second law has two statements. First is the Kelvin-Planck statement and second is the Clausius statement. Second law is called Clausius statement. Fine. So what it is saying? It is saying that it is impossible to develop a cyclic device which transfers heat from lower temperature to high temperature reservoir without any energy input. So it is just saying that, let's say we have a high temperature reservoir and we have a low temperature reservoir. This is the low temperature reservoir, and we have a cyclic device. So we want to transfer this heat from the low temperature to high temperature reservoir, because we know that usually heat transfer from the high temperature to lower temperature. But anyhow, if you want to transfer this heat from low temperature to high temperature reservoir, that is not possible, impossible. Okay, what is possible? So this is basically the Clausius statement. So what is possible? This is possible that we have a high temperature reservoir and we have a low temperature reservoir, we have a cyclic device, and we want to transfer some amount of heat, let's say QL to QH. For that we have to input some work, then we can transfer this low heat to the higher heat reservoir. Then QW will be equal to the QL plus W. It means we have to transfer more amount of energy to the high temperature reservoir. Fine. So here if I talk about the coefficient of this, is actually the refrigerator. This system is called refrigerator, because in refrigerator we usually want to minimize the temperature of the lower temperature reservoir, let's say our freezer. So we want to extract the heat from the lower temperature, and if we want to extract the heat from lower temperature, then we have to send it to some other source or whatever it is. So for that, if we want to transfer that heat from low temperature to high temperature, then we have to give some amount of work. In other words, we can say that because we are violating the nature's law, so we have to do some effort, that is work, because this work is the high grade energy which can be converted to force. So anyhow we are applying some force to opposing the nature's law, which is heat should be gone from high temperature to lower temperature. Fine. So if I talk about the COP of refrigerator, then it can be written as whatever COP or efficiency we are evaluating, that is the desired effect upon the heat input. So what is desired effect? Here desired effect is the lower temperature heat, how much heat we are extracting. And energy input is what? That is W, because W energy we are giving. So we can say that COP of refrigerator will be QL upon W. What is W? Because we have shown that QL is equal to QH is equal to QL plus W. So W is equal to QH minus QL. That is the COP of refrigerator. Fine. One more thing, we here we can see that very important concept, that is the equivalence of Kelvin Planck. Actually these are two persons, Kelvin Planck and Clausius statement. Equivalence. What is the equivalence of Kelvin Planck and Clausius statement? So let's say we have made a system like that. Let's say we have a high temperature reservoir and also we have a low temperature reservoir. So what Kelvin Planck was saying, that it is impossible to construct a machine which is taking the heat from the high temperature reservoir and it is converting, let's say it is engine, it is converting its whole energy to work, which is equal to Q. And what the Clausius statement is saying, it is saying that it is impossible to construct a machine which is taking heat from the low temperature reservoir and transferring it to the high temperature reservoir. Fine. That may be the refrigerator. But now suppose we have constructed the PMM2 kind of machine. What was that? PMM second kind of machine was that we have made a machine which is taking the heat from the high temperature reservoir and converting it into the work without throwing any amount of work to the environment or the sink. So let's say we have made the machine, okay, and what the Kelvin Planck is saying, that is it is impossible. So here we are violating the Kelvin Planck statement. Fine. Now but I am here assuming that okay, we have made this machine. Let's say assume that I have made this machine. So let's say I have made this machine and I am getting this work. Okay, now what I will do that because the Clausius statement is impossible, to make it possible I am transferring this heat to this reservoir. So what I will get, that finally I will get like this system, that engine will transfer work which is equal to Q, and it will transfer heat here from here. Let's say it is Q dash, because this is different, this may be different, then this will be Q dash plus plus W, which is equal to Q. Fine. Now you can see that here, let's see what is happening actually. And this is my high temperature reservoir and this is my low temperature reservoir. So what I'm doing, that here I mean carefully try to think of this, that here it is Q amount of heat which is taking from the reservoir, and here it is Q amount of heat which is giving to the reservoir. So ultimately to the high temperature reservoir or with the source, we are not transferring any kind of energy because it is just exchange of energy. So ultimately we are not transferring any kind of energy. It means this system is something like this, that we have engine, refrigerator, I am just transferring heat from here. It is something like this, okay, that is Q, which is equal to W, and because I am transferring work to this reservoir. Fine. and how much heat I was taking from the low temperature, that is q dash I was taking. And because the q is transferred to the engine, and ultimately I'm giving th to q dash. This q dash amount of heat I am giving, upside q dash amount of heat is extracting, so it becomes q dash plus w, it will be total q. Fine. So ultimately if you will see totally here in this whole system, if you construct, then we can see that it is just a system made like that. Here we have a system, and it is taking heat from the low temperature reservoir and transferring heat to the high temperature reservoir, and that is the violation of Clausius statement. Okay, so now we have got that when we have violated the Kelvin-Planck statement, then simultaneously we are getting that we are also violating the Clausius statement. So that is the beauty of the second law of thermodynamics. And similarly, we can prove that the violation of Clausius statement leads to the violation of Kelvin-Planck statement. Hence, these two statements are called parallel or equivalent statements of second law. Thank you.